Before we move full steam into the next section, I want to emphasize something that might be getting lost in all of the rules, and that is sort of what's the whole reason behind doing this, behind giving these strange names to these molecules. And again, I've mentioned this in the past, but I'm a little worried that it might be getting lost in all of the details. So the idea here on this slide is that there are 4 different molecules drawn. And these molecules, although they may look similar, although they may have the same simple formula, they're not the same. Even though all of these molecules have 4 carbon atoms, here's carbon 1, carbon 2, carbon 3, carbon 4, they also all have the same number of hydrogen atoms. They also all have 2 chlorine atoms. Even though they have the same simple formulas, they aren't the same. The atoms are attached to each other in different ways. And because of that, they're completely different types of molecules. They have different behaviors, they do different things, and because they are different, people have tried to devise ways of describing them so that you know exactly which one you're talking about. So one of those ways, which we've gone over earlier, are these skeletal structures. And so you can see 4 skeletal structures and they show 4 different molecules. The other way, which we've gone over in the previous section and which we will continue to go over in the next couple of sections, is to give each of these different molecules a unique name so that it's clear, even when you just write the name, you know which one you're talking about. And so that's the whole point of sort of learning these naming rules, is to realize that people came up with these naming rules so that you can just write this name out or you can speak it and people will be able to figure out which one of these types of molecules you're talking about. Another example might be if you worked in a chemistry lab and you needed to order, let's say, this particular chemical, you might go to the vendor's website, to some company that sells chemicals, and you might type this name into the search engine at the company's website, and you would get the molecule you're looking for, and you would not get these other molecules that, even though they're related, they're not exactly what you're looking for. So the names are basically there to unambiguously describe different types of organic molecules. And just to give you one more additional lesson, this one may seem a little bit weird, they all may seem a little bit weird, but this is a butane type molecule. It's butane because it has 4 carbons. Here's carbon 1, 2, 3, 4. In this case, both of the chlorines are attached to one of the end carbons. And because they're both attached to the same carbon, the name is going to be 1,1 dichlorobutane, because both chlorines are attached to carbon number 1. In the previous section, we talked about halogen substitution. So I would show you a chain of carbon atoms that would be an alkane, and then I would substitute different halogen atoms, like chlorine, like bromine, like iodine, onto that chain, and we learned about how to name them. In this section, we're going to talk about a different type of substitution that doesn't have halogens in it. And the example, however, is going to be similar to the example that I gave with the halogens. So imagine that you have heptane. So this is heptane, and I'm drawing the carbons at the very end. And again, I'm drawing the hydrogen atoms that are attached to this carbon. I'm drawing them just for the point of making them clear. Usually you would not draw them. They would just be implied to be there. You could think of them as invisible, but here they are. So imagine that in this case I can rip out this hydrogen and I can substitute something else in its place. But this time it's not a halogen. This time it's actually another carbon. So here I have a carbon that is taking place of the hydrogen, and this carbon is covalently bonded. It has a single covalent bond to this carbon that is sitting on this corner. And because all carbons have to make 4 bonds, this carbon is making 1 to this other carbon down here on the corner. It has to be making a total of 4, so it is also making 3 additional bonds to hydrogen atoms. So the way that I'm drawing this in cartoon form here is there's a carbon down here on this corner. It is attached to another carbon up here, and this carbon is substituting for one of the hydrogens that used to be there, and this carbon that's doing the substituting also is attached to 3 additional hydrogen atoms. So this is a different type of substitution. It has a little bit of a weird name, and I'll get to the name in a minute, but if you want to think about it this way, and this is the way that I think about it, this attachment, this substitution, is a little bit like methane. So methane was the alkane that has 1 carbon, and the formula for methane is CH4. You can look that up, maybe you have it on a sheet of paper. Well, methane, the formula for methane is CH4. This thing is CH3. So it's a lot like methane, except that it's missing one hydrogen. And the missing hydrogen, that fourth hydrogen that is not on there, is that attachment point is being used to actually attach to this invisible carbon down here. So this thing, this substitution, is a lot like methane. What people call that substitution is they call it a methyl substitution, or you can say that this is a methyl substituent. So hopefully you can appreciate where this name is coming from now. It comes from the fact that the substitution is very similar to methane. If there were two carbons attached to each other off of this carbon here on the corner, then it would be called an ethyl substitution. And we'll talk about that in a little bit more detail. Again, this probably is not how you would see the molecule drawn in skeletal form. It would probably be drawn something more like this, where you just imply that the hydrogen is there. You don't draw the actual hydrogen attachment. In that case, it's just invisible, even though it's there. So this is probably more accurate, or this is the way that you would see this molecule drawn maybe in real life. You probably wouldn't see it drawn like this. And then if you wanted to strip it down and make all of the carbons and all of the hydrogens invisible, you could draw it this way as well. So what I want you to see here, though, is that we've still got this chain of 7 carbons. 1, 2, 3, 4, 5, 6, 7. But now there's a branch. There's a branch that heads to the north, and there is a carbon with 3 hydrogens attached on this branch. And this branch is called a methyl substitution. So you've got a main chain of carbons, and then you've got a branch somewhere along the way. That's just a different type of substitution. All of these types of substitutions where you actually stick carbons on, these are called alkane substitutions, and usually they're called alkyl substitutions because the YL is the suffix that you add to these names to describe what type of branch you have. So again, this may be a little bit confusing. I will try to clarify on the upcoming slides. Oh, and the other thing to point out is that, again, basically the name of the substitution in these cases depends on the number of carbons in your branch. If it's 1 carbon in your branch, then it's a methyl substitution. 2 carbons in your branch, ethyl. 3 carbons, propyl, etc., etc. On this slide, I want to talk about a substitution on the chain of 7 carbon atoms that is a little bit bigger than the one that was shown on the previous slide. So in this case, we have 7 carbon atoms in this chain over here, and however, the substitution in this particular molecule has 2 carbons. There's 1 carbon at this corner here, and then there's a 2nd carbon at the end. So because there are 2 carbons that are branching off of this chain, you would basically call this particular substitution, you would say that it's a lot like ethane because ethane has 2 carbons, and so you would call this an ethyl substitution. So, or you could call it an ethyl substituent because the substitution has 2 carbons on it instead of 1. If there was just 1 carbon substituted here instead of 2, you would call it a methyl substitution. So, and I want you to keep that in mind. So I'm about to send a mixed message now. It turns out that this particular molecule does not have an ethyl substitution because of a weird trick. And I will explain the weird trick in a minute, but for the moment I want you to just think about this as an ethyl substitution for the reasons that I just described. So there are 2 carbons branching off of this chain of 7 carbons, and 2 carbons is a lot like ethane. So at least in theory, this should be an ethyl substitution. I'll explain the trick in a few moments. So before we get to the trick, I want to sort of give you the rules for how to name substituted alkanes that also includes when your substitution is based on branches that have carbon atoms in them. So the rules are as follows, and again we'll go over the details of this and show you a couple of examples on the next slide or 2. So the first rule is to write the name of the alkane with the longest chain of carbon atoms. And that's going to be the suffix in your IUPAC name. Then, again, this should all be relatively familiar to you. Number the carbon atoms starting from the end that's nearest to the first substitution. and then to give the first part of the name, to give the prefix, you give the location and the name of each substituent in alphabetical order, and that's going to be the prefix. And just to let you know, as I'm sure you're probably aware, you're ultimately going to forget these rules sooner or later. And just because if you don't use them, and chances are you probably won't use them, but they're interesting rules nonetheless. If you don't use the rules, you tend to forget them. So I am aware of the fact that for many of you this may seem to be a little bit of a silly exercise, but there you have it. Moment of honesty. All right. So here we're back talking about this particular branch here. This branch has 2 carbons. Here's 1 carbon implied at that corner. There's another carbon implied at this end here. And this chain has 7 additional carbons. 1 here, 2, 3, 4, 5, 6, 7. And I'm going to draw it in a little prettier way, a little simplified form. This is the same molecule as this one over here on the left, except I removed the hydrogen. It's implied to be there, even though it's not drawn in this case. It's still there. And here are the 2 carbons that are branching off of this heptane. So if you wanted to name it, what you think you should do is you should number them, right? You should number the carbons starting from the end that's closest to the first substitution. So here's the substitution. There are my 2 carbons. So I should number from left to right. And number the carbons 1, 2, 3, and all the way down off to the right. And because this is 2 carbons, you basically say, well, ethane has 2 carbons, so this is an ethyl substitution on a chain of carbons that has 7 carbons in it. So it's an ethyl substitution on heptane, and the ethyl substitution comes at position number 2. It comes at carbon number 2. So most beginning students would say, well, look, that the name of this particular molecule should then be 2-ethyl heptane. And it turns out that that's wrong. And some of you may have caught the problem with that naming scheme. Many of you probably haven't, because I mentioned the rule on the previous page, but I didn't emphasize it. The real one of the rules that was mentioned, actually the first rule that was mentioned on the previous slide, said that you have to find the longest chain of carbons. Now, it's human nature, again, to want to read from left to right and say, look, the longest chain is 7 carbons long. However, if you recall from earlier in this unit, I said that the chains can bend and they can twist. And this that I'm circling here is not the longest chain of carbons. This actually is. If you start from the top here with what appeared to be the substitution, you can treat it as not being the substitution anymore. This is a carbon. This is also a carbon. This is a 3rd carbon. And if you count starting from the top and bending at carbon number 3 and going down this way, it turns out that this chain that I'm highlighting with blue numbers is 8 carbons long. It's longer than the original chain that we said was a heptane. So the longest chain is actually an octane. It has 8 carbons in it. And the actual substitution turns out to be this thing over here, this single carbon all by itself. So the weird thing is that if you go back to the previous slide, it says write the name of the alkane with the longest chain of carbons. Well, that turns out to be this chain here with a bend in it, and this can sometimes be confusing to students who are beginning to study this. And this thing, which you used to think of as carbon number 1, is actually the substitution, and this is a 1 carbon substitution, so it's a lot like methane, which has 1 carbon in it. So this is a methyl substitution on carbon number 3. And so the proper name for this molecule, using the correct numbering system, which is the blue numbering system here, is to call this 3-methyl octane. And that is the correct name. This is the incorrect IUPAC name. It's if you called it 2-ethyl heptane, that is actually an incorrect way of describing the molecule. And this molecule should actually be called 3-methyl octane. So if that's confusing to you, maybe you can review this again, or you can email me and we can discuss it. But the thing to remember is that these chains actually bend, so it won't always be what your intuition is, which is to read from left to right and number the carbons in that way. So here is a molecule that you can practice on. You can pause the video at any point and possibly use this or use your list of alkane names to try to give the proper IUPAC name for this particular molecule. So you can pause at any point, and then in a moment I will continue and explain how to name it. So here is two different numbering systems to try to number this, because if you remember, the first rule of naming these types of molecules is to find the longest chain of carbons. And one way of numbering them is to go from left to right or right to left. And if you do that and count the carbons, here's a carbon on the very end, and then there's a carbon at each corner or each bend. And if you number using the red numbers from left to right, the longest chain is 8 carbons long. So that is one candidate chain of carbons. The next chain, which is going to turn out to be the correct chain, starts near the top, it moves down south, and there's if you start numbering from the top, this carbon over here is carbon number 5, and then if you bend to the right and keep numbering, this carbon here is the 10th carbon in this bent chain that I am tracing along right now. And that's shown in the light blue numbers. So the longest chain actually turns out to be 10 carbons long. So we immediately know, if you look up which alkane has 10 carbons in it, you'll know that the end part of this particular molecule is going to have the word decane in it, because that's the alkane with 10 carbons in it. So longest chain has 10 carbons, that's shown in blue. We can ignore the red numbering system now. So again, sometimes people will look at this, people who are sort of beginning to learn these rules, and they'll say, no, I'm used to reading these things from left to right, so it must be an octane because it has 8 carbons, and then let me count the number of carbons in my branch. The number of carbons is 1, 2, 3, 4, and 4 carbons in a substitution is like butane, because butane has 4 carbons. So I'm going to call this 3-butyl octane, because the butyl group, the butane substitution, is attached to carbon number 3. And again, just to emphasize, that is the incorrect way of naming this particular molecule. And so the correct way is to number starting near the top and then moving off to the right. Now, one other question is, we know that this is the longest chain now. However, it's not immediately clear whether you should number from the top and move to the right, which I'm showing in blue numbers, or whether you should number from the right, which I'm showing in green numbers, and then move off upward once you reach the branch. And the way that we have to figure this out, there's another rule that we had mentioned previously. You're supposed to number either from this end or from this end, but you pick the end that's closest to the first substitution. Well, this is our substitution in this case. This is the branch. And so we have to find whichever end is closest to this branch. And it turns out, if we use the blue numbers, 1, 2, 3, 4, 5, our substitution is at carbon number 5 if we use the blue numbering. If we use the green numbering, our substitution is at position number 6. So following that rule, we have to number using the blue numbering system. So our substitution is at position number 5, it's at carbon number 5, and then you count how many carbons are branching off of your main chain. Well, there are 2 carbons. There's one here at this bend, and there's one here that's drawn out explicitly at the very end. So since there are 2 carbons, this substitution is like ethane, so we're going to call it an ethyl substitution. The ethyl substitution is attached to carbon number 5, and so the name of this particular molecule is going to be 5-ethyldecaine. So it should not say ethylodecane, it should say ethyldecaine. And basically the 5 means that the substitution is on carbon number 5. The ethyl means that the substitution contains 2 carbons. And the decane means that the longest chain of carbons contains 10 carbons, so it's like decane. And again, just ignore the O there. Apparently I forgot to delete a bromo, and And that's basically how to name it. This particular molecule is called 5-ethyldecaine, and it's not called 3-butyl octane. Here is another question that you can pause and try to answer on your own. This time I'm doing it in reverse. I'm giving you the IUPAC name, and I'm asking you to draw the molecule. So you can pause at any point and try to decode this name. Some suggestions, just in case you haven't paused yet. What I would do is I would look at this. I would draw the I would look at the very end of the name. It says heptane, so I would figure out what that means. I would draw the main carbon chain. That's the end part of the name. Then I would number the carbons in my main carbon chain and add the substitutions that are given in the beginning part of the name. And so the beginning part, so point number 1 says draw the main carbon chain, or the suffix of the name. So the end or the suffix of the name is heptane. If you look up heptane on your sheet, if you have a sheet, heptane has 7 carbons, so we draw a chain with 7 carbons, and here it is. And then basically we need to number the carbons. Now in this case, since we're working backwards, we can basically number it however we want. We can either number from the left or from the right. For us, it's probably easier to number from the left, so I'm going to do it that way, and I'm going to number the carbons starting here. This is carbon 1, 2, 3, all the way down to 7. And then we basically read the beginning part of this IUPAC name and place the various substitutions in the correct spots. I want you to think of these numbers as addresses. They are the address, so 2 is the address where chloro needs to go. And 2, 3 are 2 different addresses where methyl needs to go. So 2-chloro means that there's a chlorine that needs to be placed at carbon number 2. So this is carbon number 2. We're going to put a chlorine there, and there it is. There is our chlorine, which is horribly drawn because I drew it using my fingers on the computer screen, but there it is. It's 2-chloro, so that's where the chlorine is supposed to go. Then this part of the name says 2,3-dimethyl. The di just basically means that we have 2 methyl groups. One is attached to carbon number 2, and one is attached to carbon number 3. So we're going to put a methyl group we're going to also attach a methyl group to carbon number 2, and we're going to attach a second methyl group to carbon number 3. And again, it's horribly drawn, but here is my methyl group on carbon number 2, and here is my methyl group on carbon number 3. And this ugly little beast down here in the lower left is a skeletal structure for 2-chloro 2,3-dimethylheptane.